The next topic I'm using for a couple of different purposes, none of which has anything to do with what's actually in chapter 2 in your book. Okay? We're going to start studying energy. Okay? As it relates to chemistry. It's going that the energy piece is going to pop up at various points in time throughout the year for different reasons. You guys studied energy, I think, in physical science a little bit, but maybe, I know you did kinetic and potential. Yes? Okay. Probably did conservation, which you've been doing since about 4th grade or something like that. Did you guys do anything with heat? Energy is heat. There's all kinds of forms of energy. Heat energy, electrical energy, chemical energy, or why?
Issue physics too.
Oh, you're already in that.
Yeah.
So you did thermodynamics.
Yeah.
This is going to be boring.
Okay.
No, actually, interestingly enough, even my AP chemistry students, even that because when I used to teach physical science, I used to teach this stuff, and then we get it in chemistry, and then we get it in AP chemistry, and even by then they were still kind of a little. Energy is heat. Energy is heat is kind of a weird thing to study because you can't see it. All you can see is the results of it. You can't even see that. You can detect the results of that. And which leads me to this story. There's a couple stories here as the introduction. One, for years, I'll wait till Grace is done. Is it okay if I interrupt?
It's okay. I'll put it in slides. Next time though.
Thanks. The class appreciates this. All right, moving on. Since the beginning of time, even the best, the smartest people in the entire world didn't fully understand it. People were aware of heat. You guys are fully aware of heat. And the transfer of energy as heat. Because for so many of you that when we were doing the separation lab and you guys were trying to heat up your water and everything and went to grab the ring stand at the end of the period, you detected really quickly that energy transfers from one object to another object. Okay? For a long time, because this is before science actually became science, science became science when people started taking measurements. Before that, it was philosophy, because people just thought about what was going on. So anyway, before people actually started taking measurements of some things, everybody thought that heat was a substance. They actually had a name for this substance. They called it caloric. Does that word sound familiar? What's that? Caloric.
Calories.
Calorie. That's where the word calorie comes from, which is a measure of energy. Okay. So anyway, yeah, they thought it was a substance called caloric, and this caloric flowed from a place there was an excess of it to a place there was a deficiency of it. Now, if you think of energy as heat, isn't that kind of what goes on? You have a hot object, you have a less hot object, and the energy seems to transfer from the hot object to the cooler object, right? So it seemed like it could be a substance, but nobody ever did any measurements, so nobody ever thought any differently. Well, then they started thinking, well, wait a minute, if we start measuring some things, specifically mass, if caloric heat were actually a substance, wouldn't the one object's mass get smaller and then the other object's mass would get a little bit greater? And so they started taking measurements and found out that, oh, well, maybe this isn't really a substance. But they still had this phenomenon occurring. So how do you explain that? You got to remember all these discussions were being had before anybody knew anything about atoms. Now, I know you guys learned at some point in time that some guy named Democritus kind of proposed an atom, but again, that was a philosophical thing. Well, there could be really, really tiny little things that make up everything else, but nobody really knew. And it wasn't really until about the Civil War period when people started really coming up with some experiments that kind of led towards the idea that yes, there are little things called atoms and so on and so forth. Once they figured that out, however, that's when the whole world started opening up, and I've got the perfect person in this class. And so now what I'm going to do is describe to you exactly what is energy as heat. Now, there's all kinds of different kinds of energy. I've already mentioned that. Okay, energy comes down to things that are moving. If something has energy, it's moving. So now, how can this relate to heat? Well, you guys may know this, that energy as heat flows from an object that has more energy, heat, than another object. And so it flows from the higher energy to the lower energy, okay? So, here's a little demonstration I do every year. I always try to find maybe the person in the class that annoys me the most. And so I'll work my way back here. And, oh, look, here's one, okay? And so here we have an object that doesn't have much energy, okay? You can kind of tell because it's stationary, not moving very much. Yet over here, I have an object that has a lot of energy, a lot of heat, okay? And so how is this object going to transfer any of its energy to this object? Is it going to happen now? Is it happening? Or is this object moving? No. Is this object moving? Yes. Well, how's the only way that this object can transfer its energy to this object? By touching it. Okay, so now what happens? Now all of a sudden this object starts moving a little bit. What happens to this object?
It starts moving less.
It starts moving less until, when does the transfer stop?
Is there a
When both objects have similar or the same energy, right? Okay, so you guys get that. That's that law of conservation of energy thing, okay? So that's what energy as heat is. It's particles, atoms, molecules, whatever you want to call it, moving, running into other atoms and particles, causing them to start moving also, and that process is going to occur until they're both at the same time. Okay? That's what energy is, or heat as energy is. But then I want to start talking about different objects' ability to absorb energy. It's called heat capacity. Different objects have different abilities to absorb energy as heat before they start changing temperature. You guys are all very familiar with at least two examples of this, and I'm going to go through both of those right now. Does anyone have a tile bathroom floor? Probably many of you, or have been near a tile bathroom floor, a kitchen floor, tile floor, okay? And those of you that had your hands up, how many of you also have like a carpeted bedroom or hallway to the bathroom and or the kitchen or whatever, right? Most of you, okay. So, some cold winter morning, you guys wake up and you roll out of bed, you put your feet on your carpeted floor. Do your feet all of a sudden feel really, really cold? Do they feel a little bit cold? Maybe a little bit, but for how long? Not enough for you to even bother with it, right? Your feet touch the floor, it's a little chill. No, I'm good, okay? And you stumble down to the bathroom, eyes half open. You hit that tile bathroom floor, and now what happens? All of a sudden you're like, oh my gosh, this floor is so cold, right? Now, both the tile floor and the carpet have been in the same house for the last X number of years under the same conditions. They're both at the same temperature. They have to be. They're all in the same area. And it doesn't feel that way, does it? Well, as it turns out, one of those objects has a higher heat capacity, meaning it's able to absorb energy without changing temperature very quickly, versus the other one which has a lower heat capacity. Which one's which? What's that? Every person I believe I've ever asked this question of says exactly that incorrectly. The tile actually has a very high heat capacity. So let me explain what that is again. The ability to absorb energy without changing temperature. So you hit the carpeted floor. Is it cooler than you? You're 98 degrees Fahrenheit. Is the carpeted floor cooler than you? Yes. But does it stay that way very long as soon as your foot hits the floor? No, that energy gets transferred to it very quickly, and the carpet absorbs what little bit of energy it can, and then changes its temperature. All that extra energy goes to changing its temperature. So it has a very low heat capacity. And you walk down to the tile floor though, and you initially step on that tile floor, and it feels incredibly cold. because it takes a while for it's able to absorb a lot of that energy before its temperature changes. Now, if you stand there long enough, does it feel okay? Yes. It just took a while because it had a high capacity of absorbing the energy before its temperature changed. Eventually, it reached that capacity, and now its temperature started to increase to match yours. Does that make any sense? Okay. There's another substance that you guys are incredibly familiar with that also has a very high heat capacity. In fact, it's one of the higher heat capacities. Have you ever tried to boil water before? How'd that go? Did it happen very quickly? Sure, you guys have all done this before. Okay, you want to make your little macaroni and cheese or ramen noodles, whatever you guys make, okay? Fill up the big pan with water, put it on the stove, turn it up to high. You're in a hurry, you keep coming back and checking it. Do you touch the side of the pan?
No.
Why not? Because it's hot. Have you ever dipped your finger in the water to see if it was getting hot yet? Who's done that? Maybe Gracie, raise your hand. Okay, great. Was the water hot? Or was it to the point where it was burning you? No, it was warm, but it wasn't hot. You said you wouldn't touch the side of the pan, because that would be dumb, but you could touch the water and survive. Why? They're both subjected to the same heat source. Which one has the higher heat capacity? The water. It's able to absorb a lot of that energy without changing temperature, whereas the metal actually has a very low heat capacity. That's why a metal is considered a conductor of energy, because it can take that energy and pass it along to something else very quickly. Water is a very good insulator, okay? Because it's able to absorb a lot of that energy before it passes it along to something else. Does that make any sense? In fact, that's what we're going to do as far as the lab is concerned really, really soon next week. We're going to take those same metals, which all have relatively low heat capacities, but we're going to find the heat capacity of each of those metals. Okay? We're going to heat them up to a certain temperature and then find out how much energy they transfer to some water. And that's why I was mentioning the whole water and energy thing. I feel like there's about 30 seconds left.
No, you got 5 minutes.
Do I really? I did really well. Let me talk to you about this then. There is no such thing as cold. Cold. There's just less heat. I have a great example of that. You guys were born like what, 2000-ish? Give or take? Okay. So you guys probably hadn't had this much experience. What's the coldest air temperature you guys have been subjected to that you remember? Negative what?
20.
Really? Where?
Here. Like 2 or 3 years ago.
No.
I was in Minnesota.
Okay. Well, when I was up in my last school district before I got here, we had a couple of nights where the temperature got down to -26 for 2 nights in a row. -26. The high temperature each of those days was -10. It felt warm. Now think this through. That was about a 16-degree temperature change, right? At night, on a normal day, average day, even when we were getting into the 90s, we were getting what, 91, 92 degrees and that kind of thing, okay? What was it getting down to at night? 70, 69, right? So 13, 14 degree temperature difference. Was there a big difference between 90 something and 70? Could you tell a difference? Right. You could definitely tell a difference between -26 and -10. That was weird, but it felt warm during the day at -10. Where I'm going with this is, there is no such thing as cold. Cold is just less energy, less heat, okay? So when you guys walk in here and say it's cold in here, no, it's just less warm. Remember that. It's still warm.
It's chilly.
It's just less warm. Right, Cielo? Hi, glad to see you can make it today. We have a quiz tomorrow.
I heard about it.
You heard about it?
Yeah.
Okay. All right, well, we'll stop there. We'll get into the calculation piece of all this as soon as we can.